a great pleasure to speak at workshop, especially because it's my first public speaking, especially in English. If you have any questions, it would be grateful if you could leave them until the end. Anyway, let's start. And today I would like to give you a general overview of theoretical analysis of local clustering coefficient in preferential attachment graphs. And let me start with the plan. First of all, I'd like to give you a general overview of models based on the preferential attachment idea and show you some examples of graphs which belongs to preferential attachment idea. Next, I will show you some theoretical analysis of a general case, especially of the local clustering coefficient. And finally, I give you some conclusions. Let me start with well-known properties of real networks. First of them, it is degree distribution. As you know, in real world networks, we have a parallel degree distribution, and it's very simple, and it's well-known. Next, two key properties and two key definitions. It is a global clustering coefficient. It's very simple. It's only triple number of triangles in our graph divided by number of pairs of adjacent edges in our graph. But the local clustering coefficients, and it's much harder to understand, but it's only one divided by another, where one it is the number of edges between the neighbors of a given vertex, and another it is the number of pairs of neighbors of a given vertex. So divide one by another, we can calculate the local clustering coefficient for a given vertex, and then we can calculate the average local clustering coefficient. So now I want to show you the well-known basic ideas of preferential attachment. As you know, usually we start with a small graph, and at every step we add a new vertex and m edges. And the main idea that the probability that a new vertex will be connected to a given vertex is proportional to its degree of given vertex. We formalize these ideas and we get a PA class of models. We also start with a small graph, and we also add at each step a new vertex and m edges, and we want to PA condition to be satisfied. It means that the probability that the degree of given vertex increases by 1 equals the following expression. And we also want to the following condition to be satisfied. We want to that the probability of adding a multiple edge is very small, and it is a main idea of preferential attachment. As you can see, because we add at each step m edges, and the probability that the degree of given vertex increases by 1 equals the following expression, it's easy to see that we have such condition. And basically we have only two parameters. First of all, it is the number of edges which we add at each step. And second, it is the a parameter, which less than 1 and more than 0. And if a equals 1/2, we have b is equal to 0, and we have the well-known model, as you know. Next, we should define a T subclass. It is a subclass of preferential attachment models. And it is a subclass where we satisfy the triangle's property. It means that the probability that the degree of two given vertices increases by 1 is equals such expression. It means that at each step we add is about d triangles. Next, I will show you some examples of graphs which belongs to PA class of graphs. First, I'd like to start with a well-known model which is suggested by a lot of authors. And we fix some positive parameter a. We start with one vertex and m loops. And as usual, we at each step we add a new vertex and m edges, and we add edges one by one. And the probability to add an edge and a given edge to a given vertex at each step is proportional to in degree of a given vertex and plus a multiplied by m. It's quite clear because to understand that its model belongs to a PA class model with such coefficients. Next, I will show you random Apollonian networks. It is another example, and it's very amazing because it's difficult to understand why this model belongs to a PA class. Anyway, we start with a complete graph on 3 vertices. At each step, we add a new vertex inside the triangle and connect it to each of vertices which belongs to our initial graph. On the second step, we also add a new vertex inside one of the triangles which we have, and also connect which vertex to all of the vertices of a chosen triangle. Next, we continue the process, and finally we have a graph which also belongs to PA class models. And as you can see, for example, because we at each step we add 3 triangles, we have a triangle property with d equals 3. Let me show you the next example. We called it the polynomial model. We assume that m is even. We fix 3 parameters, alpha, beta, and delta. It is the probabilities of events, and sum of which parameters is equal to 1. And as usual, at each step, we add a new vertex with m edges, and we add m edges in p steps because m is even. So alpha is the probability of n-degree preferential steps. It means that we choose 2 vertices by this its in-degree. So beta is the probability of edge preferential step. It means that we choose random uniformly one edge and side to endpoints of a given vertex to its edge endpoints. And delta is a probability of random step, which means that we chose a random vertex by in-degree. So it's quite clear to understand that we have finally we have a graph which belongs to a PA class model with such parameters, and we have it's very important that we have a constant global clustering coefficient, but only if a more than 1/2. It equals to when gamma in power law degree distribution more than 3, and it stands and the global clustering coefficient tends to 0 for a less than 1/2. Now I want to present you some theoretical analysis, and I'd like to start with as usual, I'd like to start with the number of vertices of degree D. So we have expectation and concentration. Now about expectation, it's quite clear. We have such expectation of n sub n of D, and as you can see, it's linear by n, and we have the power law degree distribution with parameter is equal 1 plus 1 over a. Now about concentration, it's quite clear if we use the Azuma theorem, it's quite clear to understand that it's quite clear to prove that if D is quite small, then the difference between the number of the number of vertices of degree D and its expectations difference is very small. Now, what's about clustering coefficients? First of all, what's about global clustering? To estimate the global clustering, as you remember, we should estimate first p sub 2 of n. It is the number of all paths of length 2 in our graph. It's quite clear, and as you can see, if a less than 1/2, p sub 2 of n asymptotically behaves by the function which linearly by n. Second, we should estimate the number of triangles in our graph. As you remember, at each step in preferential attachment models, we add a constant number of triangles, the D triangles, and after n steps, we have the D multiplied by n triangles. And divide 1 by another, we can calculate the global clustering coefficient. And as you can see, if a less than 1/2, we have a constant global clustering coefficient. But if a more or equal than 1/2, we have a global clustering coefficient which tends to 0. Now, what's about average local clustering coefficient? It's quite clear to understand that we have some bound of its characteristics, because at each step we add a new vertex. The degree of a new vertex is m, because we add m edges, and as you remember, we also add D triangles, and each of its triangles on the vertex on the new vertex. And if we change the sum of all vertices by the sum of vertices which have the degree is equal to m, we have such bound. Now, what's about local clustering coefficient for a given vertex? First of all, I'd like to define which characteristics. It is a number of triangles. Let's look at all vertices of degree D, and let's look at triangles which on the vertices, on all vertices of degree D. So let T sub n of D be the number of vertices on the be the number of triangles on the vertices of degree D, and n sub n of D, as you know, it is the number of vertices of degree D. And local clustering coefficient, it's the number of triangles divided by the number of vertices and divided by D multiplied by the D minus 1 divided by 2. So to estimate, as you remember, we already have the number of vertices of degree D, and we should estimate the number of triangles on the vertices of degree d. So first of all, what's about expectation? We have a function which is linearly by n, and asymptotically we have such behavior. Now, what's idea of a proof? It's quite simple, because at each step before we add a new vertex, we have some triangles on the vertices of degree d. After we add m each, some of the vertices of degree d will be vertices of degree d plus 1, so we have such term. And some of vertices which was the vertices of degree d minus 1 will be the vertices of degree d. And so we have such term. And of course, we also can add a new triangles to the graph. It is a way when we add an edge to the vertex of degree d minus 1 and to its neighbor. And so we have the latest term. And also we can a lot of small terms. I don't show you them because they are very small. Because as you remember, in preferential attachment graphs, we have the second condition that the probability to add a multiple edge is very small. So next, we prove that the expectation of number of triangles on the vertices of degree d is equal such expression by induction. So what's about concentration? As with the number of vertices of degree d, we have if d is quite small, we have that the difference between the number of triangles on the vertices of degree d and its expectation is quite small. So idea of a proof is very standard. We also can use the Azuma Theorem, and we should to do is we define the x sub I of d as such expectation, and note that the x sub 0 of d is the expectation of the number of triangles on the vertices of degree d, and x sub n of d is the number of triangles on the vertices of degree d. And it's quite clear that x sub n of d is a martingale, and only we should to do that to use the Azuma theorem we should to estimate this difference. And it's quite clear because as you remember, I mentioned before that we have a recurrent formula for the for the expectation of the number of triangles on the vertices of degree d. And if we get the difference between two such recurrent formulas, we can estimate the error, and it's quite clear to understand that we can get the result. So now if we get the number of triangles on the vertices of degree d, we get the number of vertices of degree d, divide one by another. We can get the result. We can get the local clustering coefficient, which asymptotically behaves as 1 over d. And it's very interesting because in real networks, we have a power law degree, power law distribution of local clustering coefficient. And now we have a power law distribution, but only with parameter is equal to 1. So let me highlight some basic ideas in my presentation. In generalized preferential attachment, first of all, we have a power law degree distribution, but only with the gamma more than 2. We have a constant global clustering coefficient, but only if a gamma more than 3. We also have the constant average local clustering coefficient, and a new result, we have a local clustering coefficient asymptotically behaves as 1 over d. This is all. Thank you very much. You can ask me some questions.